Hello students, welcome to EPG Pathshala. I am Sumalay Roy from the Department of Physics and Astrophysics of University of Delhi. Today we are going to talk on module 3-dimensional square well potential under the paper Quantum Mechanics. After completing this module, the students will be able to, number one, learn the solution of a 3-dimensional Schrodinger equation in the presence of a spherically symmetric square well potential. He or she will be able to know that while the radial part of the wave function in the interior region is determined by spherical Bessel function, the exterior region on the other hand is governed by Hankel function of first kind. The number 3 point that he or she will learn the solution of the transcendental equation to obtain the energy levels for the bound states. The student will be able to study the expansion of a plane wave in a spherical polar coordinates. Schrodinger equation for square well potential. Let us consider as the next example of central potential to analyze a 3-dimensional spherical square well of depth V0 and range A VR equal to minus V0 when R is less than A and equals to 0 when R is greater than A. Here V0 and A are two positive constants. The square well potential and the corresponding effective potential defined in the preceding module as V effective R, which is V subscript EFFR, equals to VR plus L into L plus 1 by 2mr square are shown in the next slide. Since V0 vanishes as R tends to infinity, solutions U, EL, R of the radial equation minus h bar square by 2m into d2u EL R by dr square plus V effective R into UELR equals to EUL as a function of R. In this slide, we have shown two figures. The figure A, there is a spherically symmetric square well potential of depth V0 and range A. So on the y-axis, we have plotted VR. On the x-axis is the radial distance R. So you can see this is a square well kind of potential which goes up to minus V0 and up to a distance A, where R equals to A. This is the same as the square well potential we have learned in case of one-dimensional square well potential. Now, the corresponding effective potential is plotted in figure B. Now, if you see figure B, on the y-axis we have plotted V effective R. On the x-axis we have plotted the radial distance R. Now the second term, which is for the V effective, is given by VR plus L into L plus 1 by 2ms square. The second term is basically 1 by R square form and it falls off with R as shown in the curve. So when R tends to 0, it diverges. That means it goes to infinity, and with the increase of R, it falls asymptotically. So that is shown by this L into L plus 1 into h bar square by 2mr square curve. Now we have the spherically symmetric square well potential superposed on it, which starts from minus V0 and ends up to R equals to AR. Now if we superpose these two, that means the V effective R, which is VR plus L into L plus 1 by 2 mr square, which is shown by the black line, is something in between. That means it first takes the diverging value for r equals to 0, then it takes a negative value, goes down to the negative. At r equals to a, it becomes again positive, and for r greater than equal to a, it follows the curve L into L plus 1 by h square by 2 mr square. So that means for r less than a, it is an attractive potential for except the r equals to 0, and for r greater than a, it is a repulsive potential because it is a positive. So the effective potential has two parts, r less than a and r greater than a, and which is given by Vr plus L into L plus 1 by 2 mr square. The radial Schrodinger equation for E greater than equals to 0 will have an oscillatory behavior at infinity and will be acceptable eigenfunction for any non-negative value of E, which is energy. We would therefore have a continuous spectrum for E greater than equals to 0. We shall study the corresponding unbound states for this case in the module where we shall be studying the collision phenomena. Here we will only be interested in the bound states for which the energy is within minus V0 to 0. That means minus V0 is greater than equal to E greater than equals to 0. As the potential 24.1 is central, we know that there exist solutions of Schrodinger equation of the form psi m L m E as a function of r, r E L r, y L m theta phi. The radial functions r E L r are the solutions of the differential equation. Wave function in the interior region means r less than a, and minus h bar square by 2m into d2 dr square plus 2 by r ddr plus L into L plus 1 h bar square by 2m r square into r into ELR is equal to E into R EL as a function of r for r greater than a. The solution for the wave function in the interior region r less than a. Let us analyze the equation 24.5a to find the solution in the region of potential well r less than a. Defining the quantity k equals to square root of 2m by h bar square into E plus V0 and changing the variables to rho equals to kr and writing RL rho equals to REL R. We find 24.5a satisfies the spherical Bessel differential equation d2 dr square plus 2 by rho into d d rho plus 1 minus L into L plus 1 by rho square to RL rho equal to 0. As in the case of free particle, the condition that RL rho must be finite everywhere, including the origin, restricts us to have RL rho equals to JL rho. That is, the spherical Bessel function as eigenfunction inside the well RL rho equals to A JL rho, where A is a constant. Wave function in the exterior region, that is R greater than A. Let us now turn to equation 24.5b, which holds outside the potential well R greater than A. This equation is formally identical to the free particle equation, except that we must remember that here E is less than = 0. Accordingly, we define lambda equals to minus of 2me by h bar square to the power half, so that E equals to minus h bar square by 2m into lambda square. In order to put 24.5b in the form of spherical Bessel equation, we must now redefine the variable rho to be given by rho equals to ikr, which amounts to replacing k by I lambda to get the Bessel differential equation 24.7. It is important to note that since r greater than a in 24.5b, the domain of rho does not extend down to 0, so that there is no reason to limit our choice to the spherical Bessel function JL rho, which is regular at the origin. Rather, we have to look for more general solution, a linear combination of JL rho and NL rho. In fact, a general solution of this equation can be written as a linear combination of these two functions, called as spherical Hankel functions of the first kind and second kind, defined as HL1 rho equals to JL rho plus I NL rho, and HL2 rho equals to JL rho minus I NL rho, which is equal to HL1 rho to the power m. Using the asymptotic behavior of JL rho and NL rho, we can also write the asymptotic behavior of the spherical Hankel functions given by admissible solution inside the potential well. HL1 rho when rho tends to infinity equals to minus I exponential I into rho minus L pi by 2 by rho, and HL2 rho when rho tends to infinity I exponential minus I rho into minus L pi by 2 by rho. Using the asymptotic formula 24.11a and 24.11b with rho equals to I lambda r, we see that for large r, the functions will increase exponentially, like exponential lambda r by r, and must therefore be excluded. The only admissible solution is HL1 IKR, which is proportional to exponential minus lambda r by r for large r. Hence, the desired solution of 24.5b inside the potential well is RELR B HL1 I lambda r equals to B into JL I lambda r plus I NL I lambda r, where B is a constant. Here we write the first three L equals to 0, 1, 2 Hankel functions using the forms of corresponding Bessel and Neumann functions. Energy levels. H01 as a function of IKR equals to 1 minus 1 by lambda r exponential minus lambda r, and H1 1 IKR equals to I into 1 upon IKR plus 1 by k square r square into exponential minus lambda r. H21 IKR equals to 1 upon kr plus 3 by k square r square plus 3 by k cube r cube into exponential minus lambda r. Energy levels. The energy levels are obtained by requiring that the eigenfunction and its derivative are continuous at the boundary, the r equals to a of the potential. This is analogous to what we do in the one-dimensional case. In other words, we require that the logarithmic derivative 1 upon r el into d r el by dr must be continuous at r equals to a. By applying this condition to the solution in the interior 24.8 and exterior regions 24.12, we get d jlkr ddr by jlkr equals to d hl1 kr dr by hl1 kr at r equals to a. Conditions on the existence of bound states. This transcendental equation is quite complicated for arbitrary values of L. However, for L equals to 0, we find using 23.24a and 24.13a that this reduces to the equation k cot kq equals to minus lambda. This equation has already been studied for the one-dimensional square well, thus setting xi as a k into a and eta as lambda into a. And using 24.6 and 24.9, we have to solve the equation xi cot xi equals to minus eta, with xi square plus eta square equals to 2m by h bar square into v0 into a, which is equal to gamma square, where gamma is equals to square root of 2m v0 a square by h bar square. Is the strength parameter of the square well. From what we have studied for one-dimensional case, we deduce that there is no bound state for gamma less than equal to pi by 2. L equals to 0 if but there is a bound state if and so on. The radial functions r, e, 0 as a function of r are illustrated in figure 24.2 for a square well with lambda equal to 6, which can support two L equals to 0 bound states. This slide shows plot of two radial eigenfunctions r el0r and r20r versus r by a. Both of them starts from 1 and extend up to 1.5 approximately. Expansion of a plane wave in spherical harmonics. We have seen that the plane wave states, which is psi k as a function of r vector, equals to c into exponential I k vector dot r vector, where c is a normalization constant. These plane wave states are simultaneous eigenfunctions of the free Hamiltonian, which is given by h equals to minus h bar square by 2m into del square, and of the linear momentum operator p equals to minus ih bar delta. They are characterized by the well-defined momentum vector p and by the energy E equals to h bar square k square upon 2m. It is quite often convenient to express the plane wave in forms of spherical wave states of well-defined angular momentum, which are characterized by the quantum numbers L and m. In the preceding module, we have seen that eigenfunctions of the free particle in spherical polar coordinates can be represented as psi elm as a function of radial vector r equals to c into jl into kr, jl as a function of kr, ylm as a function of theta and phi. Since both plane wave state 24.19 and the spherical wave states 24.20 form a complete set, an arbitrary state can be expressed as a superpositions of either of them. In particular, a plane wave exponential I k dot r can be expanded in terms of spherical waves. Thus we may write exponential I k dot r equals to sum over L equals to 0 to infinity and sum over m minus L to L CLM JLKR YLM theta phi, where the coefficients CLM must be determined. In order to do this, we first consider the special case where the vector k is taken along the z-axis, so that exponential I k dot r equals to exponential I k r cos theta is independent of phi. The expansion 24.1 then reduces to exponential I k dot r equals to sum over L equals to 0 to infinity AL JL KR PL cos theta, where PL cos theta are Legendre polynomials. The coefficients of this expansion can be determined in the following way. Using the relation integration -1 to +1 PLW PL prime W dW equals to 2 into 2 by 12 plus 1 into delta LL prime. We express 24.22 as 2 by 2L plus 1 into AL JL as a function of KR equals to -1 to +1 integration exponential IK RW PLW dW, where we set W equals to cos theta. Integrating by parts, we find that 2 by 12 plus 1 into AL JL KR equals to exponential IKRW by IKR PLW within the limit W equal to -1 to +1 minus integration -1 to +1 exponential IKRW by IKR into dDW of PLW into dW. Let us now examine this equation in the limit of large R. Using the asymptotic expression, which is JL rho, when rho tends to infinity, it's 1 by rho into sine rho minus L pi by 2. And observing that the second term of the right hand side of 24.24 is of the order of r to the power -2, by performing a second integration by parts, we find that in the large R limit, this equation reduces to 2 by 12 plus 1 into AL into 1 by KR into sine KR minus L pi by 2, which is equal to 1 upon IKR into exponential IKR PL as a function of 1 minus exponential minus IKR PL minus 1, which is again equal to 1 upon IKR exponential IKR minus 1 to the power L exponential minus IKR. On comparing both sides, we get AL 12 plus 1 I prime I to the power L. Thus, the expansion of a plane wave in terms of Legendre polynomials is given by exponential I k dot r equals to sum over L equals to 0 to infinity 2L plus 1 I to the power L J L K R P L cos theta. Now using the addition theorem, according to which PL cos theta equals to 4 pi by 12 plus 1 sum over m equal to minus L to plus L YLM star as a function of theta 1 phi 1 into YLM as a function of theta 2 and phi 2, where theta 1 phi 1 and theta 2 phi 2 represent the polar angles of unit vectors k and r. Thus we get the final expression for the plane wave as exponential I k dot r equals to 4 pi sum over L equals to 0 to infinity sum over m equal to minus L to plus L I to the power L, J L as a function of KR, Y LM star K and Y LMs R. So students, let's now summarize what we have learned in this module. We have learned the solution of a three-dimensional Schrodinger equation in the presence of a spherically symmetric square well potential. We know that while the radial part of the wave function in the interior region is determined by spherical Bessel function, the exterior region, on the other hand, is governed by Hankel function of first kind. We have learned the solution of transcendental equation to obtain the energy levels for the bound states. We know the expansion of a plane wave in spherical polar coordinates. Thank you.